In this problem, we have a heavy rope dragged along a horizontal surface, and this rope actually feels friction. I have a coefficient of friction of mu k, and the goal here is to find the tension in the rope at a distance of x from the right end of the rope. Now we're given that an external force of capital F operates on the right end of this thing. The total mass of the rope is capital M and the length is capital L. And I just recently wrote this problem for a physics exam. It was intended to be one of the harder problems on the exam. And the results of this really surprised me at the end. So it turns out at the end that the tension is going to be completely independent of the coefficient of kinetic friction. And in retrospect, we can see why that makes a lot of sense. So I'll have a few comments on that at the end of the problem. So for now, we just want to go ahead and try to find that tension. And that starts by being able to say what the acceleration of the entire rope is. And then we'll know the acceleration of the piece that's left of this cut line. And because the tension in the rope is responsible for accelerating that piece that's left of the cut line at a distance of x, that's how we're going to get a grip on this thing. So first, find the acceleration of the entire rope. So we start by looking at a force diagram for the entire rope. So I put the force of gravity into the diagram, and that's capital M times G, and the normal force. And because there are no other forces acting vertically in the problem, the normal force is just equal to capital mg. And then we have the friction force pulling left on this rope. Now that operates over the entire length of the rope, but it all adds up to a friction force of mu k times the normal force. So that's going to be mu k times capital mg. So now we apply Newton's second law to the entire rope, and I have a capital F, this applied force on the right end of the rope, minus the friction force mu k big M g. That's all going to be equal to the size of the mass, big M, times this acceleration, and that's what we're after. So we divide both sides by big M, and we find that the acceleration is big F over big M minus mu k times g. So now again, what we're going to do is switch our focus to just the little chunk of the rope left of this cut line at a distance of x from the right end of the rope. The force to the right on that is the tension in the rope at the location x. So that's what we're after. And we're going to start with a force diagram. So I've called the mass of the rope left of the cut line little m, because it's just some little fraction of the overall rope. And the weight here is going to be little mg. The normal force, again, is just going to balance that. It's going to be little mg. And then I have a friction force pulling to the left, and the tension in the rope at the location x is pulling to the right on this little mass. So that t is what we're trying to get. So I can write that t as a function of x here minus fk, the force of friction on just that little section of the rope, is equal to the mass of that little section times its acceleration. So we can solve for t of x here, and we'll plug in some details about the friction force. The friction force is mu k times the normal force, or mu k mg. So our tension at the location of x is mu k little mg plus little ma. We can factor the little m out of this, and then we just have a mu kg plus a in those parentheses. Well, a is big F over m minus mu kg. And this is the moment where the kinetic friction coefficient cancels out of the problem. So it's going to turn out the tension as a function of position along this rope doesn't depend on the kinetic friction coefficient at all. It could be a completely smooth floor or incredibly rough. You're going to have exactly the same tension at every location in the rope. And again, this is a little surprising, but I'm going to try to make it a little more intuitive at the end. All right, so the final thing we have to do to find a nice expression for the tension as a function of position is write down this little m in terms of the dimensions of the rope and the total mass of the rope. So we start by realizing that the length of this little section is L minus x. And that means the mass of that little section can be expressed as the fraction of the rope taken up by that little section. That's L minus x divided by L, then multiplied by the entire mass of the rope, big M. So finally, we're able to write down a nice expression for our tension as a function of position. We replace m with L minus x over L, multiplied by the total mass of the rope. And then we still have this term F over m from the parentheses there. And the big m's are going to cancel, and we get this really compact and elegant solution, L minus x over L, multiplied by big F, the applied force on this rope. So there are a couple limiting cases we should look at to make sure they make sense. One is when x is equal to 0. When x is equal to 0, we're all the way at the right end of the rope where we're pulling on it with a force of capital F. Well, that means the rope must be pulling back with a force that has a magnitude of F because of Newton's third law. So if we look at T of 0, we better get F out of that. And when I plug into my formula, I get L minus 0 over L multiplied by F. That's 1 times F. That's F. So that one works. The other limiting case I want to look at is when x is equal to L. That's the left end of the rope. And the tension at the left end of the rope, well, that's not responsible for accelerating any mass at all. So the tension at the left end of the rope better be 0. So when I evaluate T of L, I get L minus L over L, which is 0 over L times F. And I end up with 0 at the left end. So that makes sense also. So this is a good thing. But it's still a little mysterious why the kinetic friction coefficient completely canceled out of the problem. So there's a couple points about this that I want to make. First of all, I notice in our acceleration equation that the acceleration is F over big M minus mu kg. This means the bigger the kinetic friction coefficient gets, the smaller the acceleration gets. So if I think to myself, like, turning up the kinetic friction coefficient should increase the tension at every point, it's not so obvious, because if I turn up my kinetic friction coefficient, the acceleration goes down. So yeah, this tension is now responsible for dealing with a bigger kinetic friction force on this little section on the left, but it doesn't have to produce as big of an acceleration anymore, and it turns out those two effects exactly cancel each other out. So that's the first point, basically trying to argue that it's plausible that this works out perfectly. Now I think the second point is a little more specific and convincing. And the second point is these two limiting cases should definitely be true. That the tension is equal to big F at the right end of the rope and the tension is equal to 0 at the left end of the rope. Then I can say, well, the tension should decrease linearly from big F to 0 as x goes from 0 to L. And I'm totally convinced of that, whether or not there's kinetic friction, and no matter how strong the kinetic friction coefficient is, I should have a linear decrease from F to 0. Well, the only way to get that done is with this same formula, L minus x over L times F. So now it's starting to seem really clear in hindsight that we should have seen this coming, that we would have a friction-independent result in this problem. And this is a really good example of why I enjoy just writing my own questions for every exam instead of taking them from some book or whatever. Occasionally, I still get to create surprises for myself. And that joy of discovery is the whole reason I started studying physics in the first place. If you enjoyed this video or at least found it useful, check out another one by clicking one of the links on the left, or click the Zach's Lab logo on the right to explore dozens of physics and math playlists. As always, you can leave your questions, comments, and requests in the comments section below, and I'll get back to you within 24 hours. Thanks for watching Zach's Lab, and best of luck on your math and physics journey.